night we just code for our one of us when doing answers questions and shit.
What is it?
Anyone who wants to tune in, we go live to the world.
Live.
The max we've had is like 20 at a time. People watching. But I mean, this is only like the third or fourth day that we're doing it.
This is just a random idea.
Yeah.
How did you make it?
Just using the mailing list that we have 3,000.
I love to listen to you guys. I love to listen to what you're saying.
On the live stream.
Yeah, man.
It's technical.
Tune in your laptop and give us another viewer.
Yeah.
Really?
Even if you
I've got 2 laptops actually.
Oh, perfect.
I've got 2 laptops.
I don't want to grab it.
Okay, what am I doing? What is this?
Actually, bro.
Yeah.
We'll probably chill downstairs though, cause like we can't talk in the background on the live stream.
Well, are you not helping for Harry?
No, I'm helping him, but like he's gonna be teaching, and I'm gonna be answering questions in chat, and then we like,
I see.
So it's like, we'll chill downstairs.
Yeah, did you send that email out, Harry?
Yeah, should I send out from the Hacker Hustle?
Nah, just send it from ML Society just to save time.
Yeah, sounds like a fun thing. Nice word, though, huh? Nice word.
Thank you. Let's get our theme tune.
Should we play the RuneScape theme?
That might be good.
You know, every YouTube prank channel. So she breaks.
That's our actual theme. Gangsta shit. Gangsta Emir! We only do gangsta Emir, nothing else.
Yo, what did you think of? No, let me not say that on live stream actually.
Oh, wait, you said it. Oh, you're streaming now?
Of the video I showed you earlier.
That was fun.
The one I sent you. The Y Combinator one.
Fucking hell. That was fucking sick. Yeah, that was a really good video. Really well edited. It says you're not supposed to be editing or anything. Maybe they added that in after these guys to do it.
Based on 3 things, based on the feedback from other businesses, so star ratings, based on the punctuality, so the higher the better, and third one, which is the most important, based on the experiences, so that you kind of relate with the, let's say you don't want to send any random students, so like, if someone wants a forward back, you're not going to be sending someone who's going to be stuff, you know? You send them someone who's going to be doing like publishing glasses or taking food competition for the day, and let's say you have 30,000 students, 500 vacancies, and then they're posting daily.
don't think it will be too crazy, not too difficult. Yeah.
Yeah, but no, they're kind of like legit people working on it.
Legit, how is that?
Like, it's their job, basically. Like, they do
Yeah, but are they lit?
um,
That man, because it's hard to find people who know that shit. I think that, yeah,
I feel
big
like,
problem
I
is
feel like you should be, like, you should fucking get in there and
instinct. Well, I don't know, but I don't know enough about that animation stuff.
push and how to get to, well, I don't know how.
I think it, yeah, like, I think it's a real good idea,
It's
and
like 6-7 billion in a couple of years.
I think they will be massive. But like, it depends how much of a slice I can get. At the end of the day, right? Like, if I go there and they're like, oh, we don't want to give you any shares, then I'm like, okay, then I don't want to dedicate my life to this company.
What Tesla are you getting equity?
It all depends.
There's an intern there as well. So
Yeah,
it's
I'm an intern, but like, it really depends on how much they like me, right?
Yeah.
Like I'm not going in there with the attitude of I want to work as hard as I can so I can get shares. That's not my attitude.
Yeah, you're
My
just there to
attitude-
learn, aren't you? Obviously.
Genuinely, like, my attitude is to just learn as much as possible so I can apply it to my own businesses.
Cool.
But if it happens, it will be fantastic.
Yeah. That's nice.
But you can really see the difference between people that have shares and people that are there.
Motivation wise.
Sorry?
Motivation wise.
Oh yeah.
Yeah,
Coming in at 9, leaving at 5.
Oh, fucking makes
Versus coming in at
sense.
fucking 6, leaving at 12 a.m. You can see the difference.
What it's like the income sharing agreement kind of thing. Once you have shares in the company, your inherent net worth is tied to the value of that company. Whereas if you're getting a salary, then it is kind of but extremely elusive.
Yeah.
Like yeah, you won't get wages before you go, but that's unlikely to happen. You know. Yeah, and the startup
I think that's
especially.
where you should be working, honestly. Like, I feel like if I had your skills, man,
You could get them, bro. You should just tune into the hacker hustle.
no, be real though, like, I wouldn't get to your level. I wouldn't be able to get to your level.
Nah, but you could learn the basic stuff you need to pretty quick. Especially the kind of like, manipulating those CSV files and being able to automate stuff where you have like hundreds of businesses, say, and you need to match them. You could do that.
I want you to do that. Yeah. Just look up the fucking movie.
And you can watch the live stream, bro. Well, the first one actually is about how to load in data and stuff. I mean, it's really
Yeah, there's literally a
It
stream of it.
depends how you feel about
Is
your
that
coding
YouTube?
skills.
YouTube.
Yeah. Okay, cool. We're gonna get started. So we got people here. So welcome everybody to day 4. Day 4, right?
Yeah, it's day 4.
Of the Hacker Hustle. And we're going to be going, to the day 4 of the month of ML. We're going to be going over loss functions today, and then I'll talk about a bit more depth on the optimization stuff, which we did before, and talk about the actual optimizers, which we're like going to tend to use in practice when we get to the deep learning stuff. So yeah, just again, if you got any questions, put them in this chat here. When it comes up, you can just enter a username to create an anonymous account there, and yeah, just feel free to ask questions as we go, and I will have that open. So, but to start with, yeah, let's just go over this. So yeah, loss functions. Remember gradient descent, which Haroon discussed the other day. So basically what we had was we had some data, these blue crosses here I've drawn, and we'll randomly initialize some function which might look like this to start with, and as we're going to try and this is just a mathematical function controlled by different parameters. So this one might have like an x squared term and an x cubed term, and then different parameters of this model will be like the coefficients of that x squared and x cubed term. Or if it was a linear model, a straight line, then the parameters would be the intercept along this output axis and the slope of the line. So basically we got these parameterized functions, and we're just trying to take them and adjust the parameters so that our model, this function, will become something more like this orange one here. So they might be the same model, just with different parameterizations. And this is a good parameterization because this fits the data quite well. So if this is a regression problem, which means we're predicting a continuous output, then we want when we give an input to our trained model, we want it to output somewhere along this orange line, because that looks like it matches the pattern of how the data is spread out. And so the way we were doing that was basically we had this loss function, which is this blue line here, and that's just a measure of how bad the model is at the current time. And we'll have a look at specifically what these functions are, but just in the next slides. But basically, they are just so depending on the parameter values of the model. So what are the coefficients of these, say the x squared and cubed terms in these functions? Depending on what those parameters are, say we're just looking at one of them. For example, again, imagine a linear model, a straight line function. One of those parameters would be the slope. So as we vary the slope along this axis here, then what we'll see is that we'll get different outputs for the loss. So if we had a parameter value here, then at that point we've got this loss. Here's the parameterization corresponding to this initial bad model, which is poorly parameterized. This purple line here. So say if we start our weights in this position, then what we'll have is we'll start off with a high loss. So that means that we've got a high error for our model, which makes it a bad model, and you can see that here because it's not fitting the data. And so what we're going to do is we're going to use gradient descent, this algorithm which we talked about before, to update these parameters such that we vary them along this axis until a point, ideally this one here, the global minimum, which has the minimum loss. And so the way that we do that with gradient descent is that we take the parameter, we take what the parameter already is, this one. So we take this value here, and then from that we're going to firstly compute the gradient of the loss with respect to that parameter. So that means at this point where we are now, what's the slope? So here you can see the slope is very steep and it's negative. That is, if we increase the parameter value, then this loss will decrease. So this is a high negative number here. So what we're going to do is we're going to take the parameter value that we've already got and move it in the negative of that direction, but proportional to some step size parameter. This is the learning rate here. So if we're moving in the negative, so this is a large negative, and we're going to adjust this parameter by a negative proportion of that large negative, we're going to move it in the positive direction, right? Because we've got negative of a negative. So that means from this parameterization here, we're going to increase the parameters, which means we'll take a step in this direction, right? So yeah, that's the step size is equal to the actual magnitude of the gradient at that point, which is a large number, multiplied by the learning rate here. So we'll just do a step in this direction, maybe to this point here, and then again, and then we'll just do this iteratively and continuously update the weights until we step down this slope into here. And so yeah, that's what gradient descent is, just to recap that. So we're using that to find the minima of some function, some loss function. But what is that function? So the one we were using the other day was the mean squared error, and this is basically the really core one you need to know for any continuous output problem. And again, just to say again, continuous output, that's a regression problem. So what is this here? This is the mean squared error loss, and what it is basically we've got some prediction from our model. So you can think of the prediction as the value of this function, whichever one it is, however it's parameterized at that certain input. That's h, the hypothesis. And then we've got some label for that example as well. So this is what I predict the value for some input should be. And so this is just the output of our function, and this is what it truly is. And we're taking a difference between those two things. So if there's a difference between what I know the value should be and what I've predicted, then that's bad, right? We want to try and make it such that these two things come together, so that our prediction ends up the same value as our label. So we take a difference, and then so the reason we don't just use the difference is because what the point of this function is that we always want it to be larger as the model gets worse. So if we didn't have this square term here, well then if the model was predicting much smaller values than the label, then this value would be negative, right? Which means that the loss would be low in that case. So when this term is negative, that wouldn't work. So we have to, or we can just one reason. Or we can square that basically. So squaring that means that everything inside this bracket becomes positive, and then as they differ, as whatever inside this bracket increases in magnitude, then the loss will increase as well. And here what we're doing is just averaging that over some mini batch of examples. So instead of evaluating every single, producing a prediction for every single example in our model, in our data set, then we'll just choose some small number m of those. So say we've got a data set of 1 million images. We don't want to have to pass 1 million inputs through our model, because that'll take ages, right? So we'll just pass a small sample through them and then average that loss in that case. So that's mean squared error, and it's pretty much the only loss function that you need to know about when dealing with regression problems. So yeah, we'll just talk about the last the binary cross entropy loss, and then I'll check if there's any questions if I haven't been notified. So, but yeah, please put questions in the chat if anything at all isn't clear. If you want me to explain anything again, if you miss anything or whatever else. So that this mean squared error, that was for dealing with continuous output problems, right? So regression problems. And there's this other loss function, which again is basically the only one you need to know for classification problems, the binary cross entropy. And so this is for classification problems. So what we have here is our prediction, y hat. Sorry, I changed the notation there. In the other slide, that was a h for hypothesis. But here we'll say y hat is the predicted value of y. And what this kind of loss function is used for is when you have a data set with labels which are binary. So imagine you have images of cats and dogs, and the label for them is either going to be a 1 or a 0, and either one of those numbers could represent different class. So let's say 1 represents this is a dog, 0 represents it's not a dog, or something like that, or it's a cat. And so this loss function, what we're trying to do is we're going to try and minimize this thing, and okay, I'll just leave it like that. Yeah, we're going to try and minimize this loss, and so that means that as the model gets worse, as these predictions differ from the true labels, then we want this thing to increase. So we need to be dealing with both cases here. Where the labels are binary, they can have 0 and 1 as a label. We need to be dealing with both of those cases. So what do we do when our output has is an image of a dog, and what do we do when it's not? So the easiest way to understand this loss function is just split it in two pieces. So firstly, let's look at this case over here, this term. So when the label, and so this is the actual label, right? The true label, y, and it's either going to be 0 or 1. So in the case where the image is not of a dog, then this will be a 0, okay? And we want this thing to be also a 0, right? So, but when this is a 0, this term cancels out. So we're not going to have any contribution to the loss function from there. But then on this hand side, when the label is 0, this will be 1 minus 0, which means that this term here will just have a coefficient of 1, which means that this term is contributing to the loss function when the label is 1. Sorry, is a 0. And what this part of the loss function looks like is a graph like this. So this is the log of the input function here, In this case, we've just shifted it over by 1 and negated it. So flipped it upside down. And what you have here, this is the point 1, and this term, as I said, is only going to be present when the label is 0. Okay? So when the label is 0, this line here, this value is added to the loss function, and when the prediction is 0 as well, which we want it to be, then this log 1 minus y hat is also 0. So there's nothing added to the loss function when the label is 0 and the prediction is 0. And again, this term has a 0 coefficient, so it's not contributing to the loss function. This has a coefficient of 1, so it is. But then as the prediction varies away from the true label at 0 towards a 1, this value, which contributes to the loss function, increases asymptotically. And so, yeah, you get that addition to the loss function. And then the other case, basically just the opposite happens. So when the label, which our model should be predicting, y, is a 1, then this term has a coefficient of 1, so this will contribute to the loss function. And then this term has a coefficient of 1 minus 1, which is 0, so it does not contribute to the loss function. So this is for when the label is positive, this is for when it's 0 or negative. And yeah, so this is just basically a slight variation on this log term here. So this negative, multiplying both those brackets, negative log of y hat is just this graph, but it's flipped upside down, so that when the label is 1, then as the prediction approaches 1 as well, then the loss, this term which contributes to the loss decreases. And as the prediction goes towards 0, when the label should be 1 and this term contributes, then the loss contribution increases asymptotically. Okay, so these slides are actually not available, but I will put them. I'll put them on GitHub now. So just let's just break for a sec, and if there's any questions, like throw them on there now, and I can answer whilst I upload to there. Yeah, please ask questions, guys. If anything's not clear at all. Cool. So if you want the link to these slides, it's right here. That'll go through. Yeah, okay, cool. So now what we can do is let's get into the code. Where were we? So make a new file, loss functions. Again, if you want to follow along, you don't have an environment set up, just go to Google Colab and then click here and create a new Python 3 notebook, and you'll be able to run all the code which I'm going to show you now. Okay. So we'll start off with some function that I found looks like this. So 0.1x cubed minus x squared plus 25. Yeah, we'll start off with that. So we're firstly going to import NumPy as NP, so to allow us to do all kind of linear algebra and array stuff, and then we'll set some input NP linspace. So that's a NumPy array across the range, let's say from -5 to 5, and it by default returns you 50. So if we print x, run that, that's what that looks like. It's evenly spaced, 50 evenly spaced numbers between 5 and -5. And then we'll say that y is equal to 0.1 x to the power of 3 minus x to the power of 2 plus 25, like that. And then we will also import matplotlib.pyplot as plt for plotting, and then we can do plt.plot. Let's do plt.scatter. So scatter plot of x against y, and then we'll show that. Run that. Cool. That's what it looks like. And now we're going to try and come up with a function to fit that. So what we'll do actually is we won't have 50 points. We'll just have 10. And we'll also do plus np.random.randn, so add some random numbers to there, 10 random numbers. I think that should do it. Yeah, cool. Alright, yeah, so now we're going to create a function, h is equal to, okay, yeah, well, we're actually going to create a class. We're going to create a class called model. And then when we create this, we're going to initialize it with some random parameters. So we'll say self dot the x cube parameter. So this is assuming that, like, okay, I've seen the data and I think I'm going to give my model an x cubed term, and I'm going to give it an x squared term, and then I'm going to try and find those parameters, right? Okay, so yeah, okay, cool. So we'll say self dot x3 is equal to np.random.randn, and that'll just give us a scalar random number, which will be the initialized parameter, the initialized x cubed coefficient in our model. Then we'll say x2 is equal to np.random.rand again, and then we'll say self dot bias is equal to np.random.randn again. So these are the weights of our model. I'm going to take in this the inputs x, which, you know, basically every single one of those points is just a single example, and then from that example we're going to try and make a prediction of what the of a corresponding output should be by modeling the relationship with this class. So we'll say def forward. So this is like the forward pass of our model, which takes in some x, and we want it to return us some y, and we want to try and predict that. So then we'll say h is equal to, so our hypothesis equal to self dot the x cubed parameter multiplied by x to the power of 3 plus self dot x squared parameter multiplied by x to the power of 2 plus the bias that we have for this model. And then we'll just return that h. So, alright, what have we got? Yeah, we don't want to show that yet. So we'll only show our model down at the bottom after we've made some prediction. So firstly, we're going to create an instance of that model. So yeah, we'll call it my model, and set that equal to an instance of this class. And then we'll do my model dot forward on x and see what the predictions are. So we'll get a prediction from that, and then we'll do again plt dot we'll do a plot this time, so we get a continuous line for our function, and we'll plot the inputs against their predictions. Okay, run that. this is what it randomly initialized as, which doesn't look too promising. And let's also, when we initialize the function, let's print those parameters. So print x cubed, parameter is self dot x3, and then x squared parameter is equal to self dot x2, and then bias is equal to self is equal to the bias. So if we run that, looks a bit better. But here you can see, so yeah, x cubed initialized as 0.38, x squared coefficient 0.67, and the bias is 0.55. Okay, so alright, now what we're going to do is we're going to create the loss functions which I was talking about. So we'll define a function to get the loss function, but in this case, right, we're going to be predicting a continuous output. So we'll say the mean squared error loss, and this is going to take in the predictions and the labels, and then we're going to return, we'll say loss is equal to, we're going to do the predictions minus the labels, and we're going to square them, and then we're going to sum them. So yeah, it's the we're going to sum the squared errors, and then we're going to divide it by the length of the predictions, right? And so this is this equation here. So yeah, I'm dividing by the length of the predictions, which is this m. I'm summing them over all of these values. So I'm summing up the m different examples difference between their predictions and their labels squared. Okay, and then we'll from that we'll return the loss. Okay. And as we did before, we actually want to be able to get the gradient from this. So we'll set a flag grad equals false by default. So by default, we're just going to return this loss. But then we'll say instead, if grad, which is like, so if that's true, then I actually want you to return me something different. So I want you to return me, let's say g is equal to, so the derivative of this, so that's going to be mp dot sum, or I mean, you know, we can even just take the code from here. Oh god, he's got a different function written in there, so let's not do that. Let's just say, okay, the derivative of this is going to be 2 times the sum of the predictions minus the labels. It's going to be 2 times the predictions minus the labels, but then we also need, if we're going to pass in the gradient, then we need to pass in the input, none by default, because then this needs to be multiplied by that input there. So if you do the maths, you'll find out like that's the equation for the derivative of this thing. So then we'll return that gradient if that gradient flag is true. Just check that's all right. Yeah, cool. That should be good. And then we can use that for gradient descent. So then we can say, we're going to say, we'll say here def update weights, update the weights, and it's going to take in the gradient. So, and firstly we'll implement a basic a gradient descent here. So yeah, cool. Well, what we're going to do is we're going to get the gauge of the parameters. So, and then we're going to take away from that. Tell you what, when we create this model, we'll initialize a learning rate as well. By default, 0.01. Let's say that was that alpha term in the gradient descent there. And so this is what I'm just going to implement here on the update weights rule. So we'll just move the weights in a direction which is the self dot. Let's just define that for this instance. So say self dot learning rate is equal to learning rate there. So by default 0.01 unless you pass something else in here. So we'll say self dot learning rate multiplied by okay, well this gradient, obviously we need to have, like, this is going to be a vector of gradients. One gradient for the rate which is going to be the rate of change of the loss function with respect to the x cubed coefficient, one with respect to the x squared coefficient, and one with respect to the bias. So I guess what we can do is oh yeah, okay, cool. So this is actually the gradient if we had a linear model, which we don't. So in our case, we're gonna have, that would have been g like x to the 1, but we don't have that. We actually have gx to the 3. So the derivative of that would change slightly. So we have 3 multiplied by the input to the power of 2, I believe. So what's that going to be? It's going to be h equals x cubed plus x squared w3 w2 yeah, okay, sorry, that's just going to be x cubed there, isn't it? So yeah, we basically did the derivative of this thing, so that took down the 2, and then we multiplied by the derivative of the inside of there. So that was the hypothesis minus the prediction with respect to the weights of the x cubed coefficient. And so what this looks like was the x cubed coefficient multiplied by x cubed plus x squared coefficient multiplied by x squared plus the bias. And so the derivative of that with respect to the x cubed coefficient is just x cubed. So that's why we've got that x cubed there. Then we're going to have g underscore x2 is equal to basically the same thing, np.sum predictions minus the labels, then multiplied by the input to the power of 2, that's going to be, and then the gradient of the bias is going to be equal to 2 times np.sum of the predictions minus the labels multiplied by multiplied by 1 in that case. So I'll write down all these derivatives and upload them to the GitHub as well, actually, because it's got a bit confusing doing this now. So we'll return these three gradients in list. So we'll return gx. We'll just return them as a what should we do? Yeah, let's return them as a list. So return gx3 and then gx2 and then gb. So that's the rate of change of this loss with respect to x3, x2, and the bias. And so, yeah, when we ask for this mean squared error loss, if we say grad is true, then we will return those three things, and then these will be used in the updates weight function to improve those weights. So we'll get that grad, and that'll be a list. So this x3, that gradient is the first element from it, so Python 0 index, so we do grad 0. We'll just copy that line, paste it a few more times, and then edit what we need to. So with respect to, so we're going to update the x2 parameter by gradient 1, and then this one by the last value there. Okay. So that should update the weights. This should give us the correct gradients and returns the loss if we don't ask for it. So now we just need to create a training loop for that. So we'll say the epochs is equal to 10. That's the number of times that we're going to go through the whole data set. In this case, I haven't implemented batching the data set, so one epoch will be just one forward pass of the whole data set. But in practice, and we'll explain it later, like what you would do is break up the data set into smaller pieces, and then pass pass all those small pieces of the data set through the model in one epoch before you then retrain again on the same data for a second epoch. So we'll say for epoch in range epochs. Then what we'll do is we'll basically get our data, and we'll do a forward pass through the model of that data to make some prediction. And then, so let's bring this down here. So firstly, we'll turn on interactive mode. So we'll turn on interactive mode for the plot. After we've shown, we won't show our first predictions there, but we'll show them just after this. So after we make our predictions, we'll show them, and then what will we do? We'll have to do. So we're gonna have to create. We're not just going to use a plot, we're going to use a figure. So we'll say fig equals plt.figure. A figure is just it's just that window that pops up when you when you do a plot anyway. So we're just explicitly creating the figure, not doing everything automatically with the plot as we do earlier or there. So on that figure we'll make an axis. So we'll say fig.add underscore subplot 111. So that's just like I want one row, one column, and this is the first plot on there. And then we will do, so we'll do all of that, and then we will do on that axis we'll plot our prediction, and then we'll do fig.canvas.draw, and that will update the plot. It'll basically draw the new stuff on the canvas, which is on the figure, and the canvas is just the stuff which you can edit, basically. Okay, cool. So let's just plot everything as good. Firstly, we'll comment out that interactive mode line, and then we'll just show the plot at the bottom there. Okay, cool. So we've got them on a different axes, yeah, because we did that with plt.scatter there. So we'll make the axis. We'll actually do axis.scatter and I'm going to call this firstly the hypothesis axis, and then this and just so I'll just update those names. And then we'll do cool, that looks good. Run that. Alright, nice. So there is our there's our model, there's our data. We're trying to fit it by optimizing the mean squared error loss, and we're going to do that using these functions here, which I wrote to update the weights. So after we have done that, just put these here. What we're going to do is we're going to compute the loss. So we'll do loss is equal to the loss function. I called it MSE, didn't I? Yeah, mean squared error loss. What does it take in? It takes in the predictions, which are our hypothesis there. It takes in the labels, which in this case is y, and we're not going to pass anything else. So by gradient, by default, the grad equals false and the input equals none. Then we'll get the grads. So the gradients of the x cubed, x squared, and bias term, and we'll do again MSE loss, hypothesis, labels, grad equals true, and then the input equals x. Okay, and then we'll do plt.pause for half a second. And then this should work going through. Okay, cool. So our model isn't updating for some reason. Oh yeah, because we didn't call update weights, did we? Cool. So then we need to do model. No, my model. Dot update weights. Takes in the gradients, so the grads like that. Run that. Model has no. Yeah, it's not x underscore b, is it? Why would it be? Okay. Okay, so when we do this, is that all right there? Yeah, cool. So let's just print the gradients here. I think what the problem might be actually is that the rate of change of the loss with respect to the x cubed term will be huge, and so we should probably lower the learning rate in that case. Okay. Still wilding. And what are they? Yeah, they're huge. Look at them. So the first gradient we computed was massive. So I'll just won't pause that for so long. Looks like it's getting a bit better. How do I remove a plot? Remove lines in matplotlib. So here, did lines.plot. What do we want to do? Lines.plot. Lines equals axis.plot. Okay, let's try this. Lines.pop 0. So obviously we need to make this variable lines our plot. So we'll say lines is equal to that, and then next time come through, we'll plot it again. There you go. Okay. All right. So let's run that for longer. Okay. Yeah. So here you can see the gradients, right? The gradient with respect to the x cubed component is much larger than the others, right? It's like it's like 20, 25 times larger than even the x squared component, and about 500 times larger than the bias term. So this is oh God, we're going to run out of time. So this is an issue which you can solve by feature scaling. So by putting all of your input features within the same range. So remember, our inputs range from -5 to 5. So when we take our input and raise to the power of 3, the maximum value magnitude it's going to have is 125. The x squared is going to have max of 25, and the bias, well, that starts pretty small. That starts around 0.9, right? And so those things, so like this, having like a massively off x cubed term, that's what's screwing things up, right? That's giving like a massive error to the loss function, because when you have that x cubed component which is wrong, the value which it contributes to the hypothesis, and hence the loss function, is massively larger than the others. So the rate of change of the loss with respect to that x cubed parameter is much larger. And because gradient descent is based on following the compute gradients for each parameter, for each parameter, well then it's going to make the step sizes for this extremely large if this is extremely large, and at least they're going to be relatively large. So by decreasing the learning rate, what we're doing is doing the step size by a smaller amount. So when we had this update rule, what we were doing, this is really large for the x cubed component, right? So when we take a step in it, if it's really large, we need to make the learning rate small enough such that it doesn't diverge, so that the step size doesn't jump all the way to the other side of the valley and then back and so forth, and just not converge down to some optimal point. So we need to increase this value, decrease this learning rate such that step size is decreased massively. The problem is that with this optimization algorithm, the learning rate is the same for all the different parameters, right? So when we make it smaller for the x cubed term, it also makes it smaller for the x squared term. But the x squared term is already, like I said, about 25 times smaller in that case than the x cubed term, which means that the step size of the x squared parameter is going to update 25 times slower, essentially. So that's why you see what happens when I run that program is that the x cubed component seems to converge quickly. Bias isn't updating there, so we'll fix that in a sec. I might get on to just explaining the rest of the algorithms firstly, and then I'll upload the latest code after. But yeah, the problem is that the learning rate for each of the parameters is the same, and hence basically the step size of all of them is controlled by the one which is inducing the most error. And so this kind of highlights, like, at least for one reason, why gradient descent is a pretty basic algorithm. And so right now, what I will do is I'll explain some more complex algorithms, which we're not gonna implement in NumPy like we have there, but we're going to be able to use really easily when we start using PyTorch, the deep learning framework, which we're going to show you how to do more advanced stuff in. And so instead of using gradient descent, you can literally just change one function in your code and use like a much more complex and efficiency optimized algorithm, which like the Facebook developers who made PyTorch have created. So are there any questions so far? Please feel free to ask. Okay, all right. Someone asked, is that a question? Oh wait, yeah, okay. Sorry for not seeing that. I'm not getting the notification for some reason. Okay, yeah. So the flipped over graph for, again, in the binary cross entropy slide. What that was. So this is the log graph, right? Sorry, I should have labeled that. This blue line is log of the input, and this horizontal axis is obviously the input. Each of these terms, they have this negative in front here, which just flips them, and so they become looking something. Well, this one directly is just negated by that sign there, and becomes this. This one is transformed slightly, but then is also negated and looks like just some transformation of that. Basically, the point being that these terms are only active when the corresponding label is true. So in this case, this part is true when the label is 1, and as is similar in the other case, as the prediction approaches the correct value, the loss decreases logarithmically in this case, and as it begins to vary more from the actual correct value, which it should be predicting, it increases to infinity asymptotically. Okay, so let's just go over these more complex algorithms before we finish up. We need to be more focused in an hour, don't we, to get stuff done efficiently. But I'm sure we'll get it. Please, give us any feedback as well. If we should have gone straight into code or done some different code or anything else, then please let us know so we can do better next time. Okay, these slides are on regularization and optimization. We'll go over that later, but yeah, I'm just going to explain the optimization techniques that we can use instead of gradient descent. Here's the basic stuff that we've already looked at. More complex example with a 2D input space and a more wavy loss function. Same thing applies though, right? You start off at some point, you adjust those parameters, which are these axes here, in a direction downhill. You can see that there. You move downhill, keep moving downhill until you reach some ideally low global optima. All right, so SGD, how does it work? So we initialize the weights randomly, and yeah, Haroon already explained this in another video, so if you want to check that out, go for it. Basically, we're going to compute the gradient by finding the derivative of the loss function. If it's continuous, that's going to be mean squared error. If it's categorical, then it'll be binary cross entropy or cross entropy. Yeah, cross entropy is basically just binary cross entropy, but for more categories. It's pretty much just as simple. So here we have the velocity component, right? And so the velocity of the parameters, basically as they move over this surface. Okay, it really isn't working, is it? What's happening? Alright, yeah, so basically we're going to start with this simple gradient descent, and we add a momentum term, which means that the update, which is this term here, is going to also have a velocity component on, and a velocity is just some proportion of the previous step size, which is this, right? So basically we initialize the velocity as 0, and then we update it. So for the first time, v will be 0, so we'll have nothing there, and the velocity will become like some, you know, like the learning rate of the gradient. So it'll just be some step size in the downhill direction. And then in the next iteration, once we've still not met the stopping criteria, we come back down to here, and now we're going to set the momentum equal to some fraction of what it was before, but then also pushed in the direction which the weights were being updated before, or the gradient of the loss with respect to the model parameters in in this iteration. But then when we do when we update the weights, we just move them in the direction of that velocity. So they're moving down the slope with some speed. Essentially, you can think of it like a rolling ball, where the velocity at the next time step is some proportion, i.e. friction of what it was before. So it's being like slowed down by some friction there, but it's also accelerating in the downhill direction by some force as well, which you can imagine as the weight of the ball. Okay, more complex algorithm, Adagrad. So this is where it starts to get interesting, because we have now, basically we're going to track, we're going to have like a dynamic learning rate for each different parameter. And so this would solve that problem that we were seeing in the code. So it's basically the same thing, right? So we initialize this variable 0, gradient accumulation variable vector, which is like the main thing about Adagrad. So, and this basically means, and what we're going to do with it, we're just going to say, well, after we've not met the stopping criteria, get a mini batch, compute the gradient of the slope of the loss for those inputs, and then basically look at where you are on the surface, on the loss surface, and then find the gradient of the loss with respect to every different one of the parameters, and then square it, so that we'll have like some positive term in a gradient accumulation variable, which corresponds to like basically the absolute slope of some absolute value representing how steep the loss is. The loss at this point, at this parameterization, varies as each different variable changes. So imagine on the first iteration we've got none of these r's here because we've initialized them all to 0. Well, the accumulation vector is basically going to store the square of the loss, of the rate of change of the loss with respect to that variable. So if you think about a 2D example where you've got a bowl, but imagine the bowl is squashed so it becomes more like a valley. Well, then in the narrow direction, the gradient is going to be very steep, but in the wider direction, it's going to change by, say, the same amount over a longer distance, so you'll have a smaller gradient. And what this term here does is it will add basically a large value if the gradient is large at that point. So in the steep direction, the narrow channel direction of the bowl, it will add a large value to this accumulation vector. Okay. But in the other direction, it will only add a small value because the loss in that direction, which is like a very more gentle slope rather than the steep slope in the other direction. This will have a let's say this is the narrow the wider direction with a shallower gradient in theta 1, and in theta 2, let's say, it's much steeper. So basically, R2 is going to be large and R1 is going to be small. This means that this term of the weight update step is going to change, and so this is a vector, and you're basically taking this part, which is originally just the learning rate, right? And for each different element, for each different parameter in the model, you're dividing the learning rate by that gradient accumulation. So if the gradient of the loss with respect to that parameter in some direction was steep, then you're going to divide the learning rate by a large amount. So in the steep direction, the learning rate there, i.e. the step size across that steep part of the loss, will be reduced by a lot because it will be divided by a large number, right? So that gradient, that parameter step size in that direction will be decreased to basically match the step size in the other direction, because in that part where the bowl is wide, then the gradient will be small, and those steps will still remain large because they haven't been divided by so much. If that's not clear, please just let me know. Please let me know anything that isn't totally clear there. And then just note we have this other term as well here. So Because these gradient accumulations are initialized as 0 on the first run. If we divide by 0 for every single model parameter, then this is going to shoot to infinity. So we have this small constant here to provide numerical stability. And so it's essentially just the same as the as gradient descent, but the learning rate is scaled by this factor. And what this is basically how steep the gradient has been over time with respect to that particular variable. So here you can say, gradient accumulator will be lower for more flat areas, so the learning rate remains high and progress is made even though the gradient here is small. Learning rate can be initialized to a greater value, and divergence will probably occur along the directions where the gradient is high initially, but the learning rate will adapt. So where that gradient is high, this value will be large, and the learning rate will be divided by a large number, and hence become small. So even though it would be diverging in one direction, what happens is it's divided by a large number, and hence that learning rate is reduced massively, so that instead of diverging, it should converge down towards the bottom of our bowl. Okay. So that's Adagrad. RMS prop is the one we're going to look at next. And it's basically the same thing, but instead of so what you notice with Adagrad is like the gradient accumulates indefinitely, so it never resets. So if you reach one steep part of the loss function, so if you're looking at the loss function and you're at some parameterization where that loss changes a lot with respect to a particular parameter, it's going to have a high gradient, which means this gradient accumulation vector is going to be increased a lot. And once that happens, it will never go back down because there's no part of this algorithm which is reducing that accumulation again. So here I missed this. The learning rate can't be recovered once we encounter a large partial derivative, which means that if we hit just one steep part, even if there's just some notch in the loss function or something, then the learning rate is going to be like decreased massively and not work its way back up. So yeah, and like even if you and what might happen is like the learning rate might be made too small before you reach like a suitable convergence point. So with RMS prop, what we do, instead of accumulating the gradients at every point continuously, we use an exponentially decaying version, right? So here, like basically the discount for the learning rate for each of the examples, for each parameter, will be some proportion. So it will be pretty close to what it was previously. So that usually this will be like 95 or something. This parameter row here. So what the learning rate is discounted by is like pretty much what it was before, but now it's also got some term which accounts for the gradient at this point. So what this means is that over time, the previous values of R, they begin to matter less, because this term is the one being contributed to the accumulation variable at this point. So basically, every time you do this iteration, you're going to come to this point where you multiply R by some value between 0 and 1. And so every time you reach this point, all the previous accumulations, they're going to be multiplied by that value. So it'll be like, let's say like 0.95 times 0.95 times 0.95. And as you have that compounding multiplication of this discounting variable with the accumulation, it means that the importance of those drops off over time. So it's exponentially decaying. So yeah, if there's any questions about that, again, please put it in the chat. I should put some visualizations here. We'll do that at some point soon. Okay. So we've also got Adam, and this is where we have not only, this is another optimizer. So this is where we have not only the discount scaling here, but we have a second parameter. And so these are called like the first and second moments. And so the second moment is to decay the learning rate, just like we've seen in Adagrad and RMS prop. But Adam is basically RMS prop with momentum. And so we're multiplying those well, basically this is the now, so we're going to compute this variable s, and what this is basically some exponentially decaying contribution of the gradient at that point. So it's like we're making the update steps in the direction of the gradient, but also contributed to by what those update steps previously were. And so yeah, and in that case, if you look back at the momentum equation earlier in the slides, this is a similar term to what you'll see there. So Adam is basically RMS prop with momentum. RMS prop is basically Adam with an exponentially decaying what do you call it, a learning rate size, and Adam is just sorry, not Adam, and Adagrad is simple gradient descent with a decaying learning rate, which increases as increases by the square of the gradient of the loss function with respect to each parameter every iteration. Okay, so that was a lot of optimization, and we'll show you how we can use these in practice as soon as we get to the deep learning stuff, which will be in about 3 days, I think. So on Sunday we'll be doing that. Is there any questions right now? Otherwise, I think we're almost there. Yeah, I'll put those slides in there as well, so you can. Well, actually, to be honest, these slides are already, if you want to check them out, they're just in the Academy of AI. So go here to my GitHub, Life Efficient, click Academy of AI, and those ones we were just looking at are these regression ones. Where is this? Regularization and optimization, that's what I mean. So yeah, check this out. Also, yeah, everyone, please put your email in here. And this is purely just so we can like keep track of who's attending the sessions, so that we'll be able to give out prizes later in the month once we've built some more into this site. And yeah, like I'll hang around for a minute. So if there's any questions, like just feel free to ask. Otherwise, thank you for attending day 4 of the month of ML. Please leave any feedback. I recommend how we can improve the sessions. Should it be more code? Should it be more theory? Should the theory be better explained? Should we be doing more complex stuff already? Do you already know this? What do you want to learn? What haven't we covered? Please let me know there, and we'll give you prizes later. All right, cool. But yeah, on that note, we'll hang around for a minute, do the outro, and then that's it. That's another day of the Hacker Hustle. invite your friends tomorrow. Yeah, we'll be going over neural networks. So pretty much the core of all state of the art AI right now. So please, invite your friends to come along and tell them to sign up to the Hacker Hustle and leave your email in the referral box on that sign up link. So that sign up link is just if you click this sign up here on the first page. So you can click there, and there's an option for leaving a referrer's email. If you get them to leave your email, then you'll be in for a treat later in the month. Okay. More people get to sign up, more likely you are to win something, and we'll be announcing like prizes and incentives soon. No problem. Yeah, you're all like really welcome. So just let us know what else we can do to make the sessions better. Why did 3 people tune in for the last minute, like post finishing? Let me know. That would be an interesting thing to find out. Why did you come back? Why did you come now? Also, follow us on Twitter. Follow us on Twitter at the Hacker Hustle. There you go, at the Hacker Hustle. Give it a follow. We don't want to spam everyone with emails, so just stay updated here. But yeah, if you do want to get an email about any session and you don't know already, all you got to do is come to the month of ML. You can see these sessions have already happened, so you can just click on them and follow that through. But otherwise, just type your email here and then enter that. It saves it as a variable in the JavaScript, and then you can just click to register interest. So if I register my interest for that one, this one's just happened. And so yeah, every night at 12, what's happening here is that there's a function in the JavaScript which checks what day of the month it is, and all of these obviously have a corresponding date. So if the date of this element is greater than the one which we're on at the moment, so at midnight tonight, it will render this button differently. It'll render it as one of these, and then during that time, oh god, I should have uploaded that. And in that time, we will have made this page, which is literally just the recording for that day, as well as the chat for that event, as well as the code. So you can just check all of that out for the previous sessions. Sorry, that one's not been uploaded right now. We'll do that now. Okay. Also, I don't know, recommend us a good intro outro song as well, if you think you can think of a better one. Okay. Hacker hustle. Peace out.